Hi everyone, this is Dhanasekaran, Assistant Professor, Department of Electronics and Communication Engineering, KS Rangasamy College of Technology. Today we're going to discuss about laser emission absorption in optoelectronic devices course. So these are the outlines of this topic, basic principles of lasers, fundamental absorption, spontaneous emission, simultaneous emission, population inversion, and application. And starting from the basic principle of laser, the term laser stands for the light amplification by simultaneous emission of radiation, and it works based on the three fundamental processes in the quantum mechanics. Before going to the fundamental process, we should know about the laser. So light amplification, simultaneous emission of radiation, the laser, in general, the meaning of intense monochromatic electromagnetic radiation in the wavelength region of light, and that is coherent to the input. So if you input light containing all kinds of frequency, only one frequency become amplified. So a laser has a specific meaning of everybody usage of the world. However, is more special. It is a device that produces the coherent beam of monochromatic light in one direction, only one. And at least for the semiconductor laser, without some input light, that is with a battery or a power source, okay, and it's an electronic oscillator that works by internally feeding back parts of the output of an amplifier to the input for a certain frequency. So coming to the quantum mechanics, so the three major process: the absorption of energy, spontaneous emission, and simultaneous emission. So the first one is the absorption of energy. The fundamental absorption, the interaction of photon with an electron in the valence band, resulting in an electron, that is C electron, and the whole pair. I'll show the image. This is the valence band, and this is the conduction band, and the V denotes the valence band, and the C denotes the conduction band. Okay, the interaction of the photon with an electron in the valence band resulting, that's electron hole pair. Okay, so in the absorption, the atoms in the lasing medium absorb the energy from an external source, that may be electrical current or optical light. Casing electrons move from lower energy to the higher energy states. So that is a fundamental absorption. And next, this is the absorption picture. Here we have the energy, and energy. Here we have a lower energy state and a higher energy state. In between, you can see the photon that is moved to a low energy state to higher energy state. The electron absorbing photon energy in the during the absorption. After absorption, you can see that the image, the low energy state and the higher energy state. In between, you have the electron jump to excited state after absorbing the photon energy. So this is the absorption function. So next one is spontaneous emission. The spontaneous emission, we can say the photon by the spontaneous and direct recombination of an electron hole pair. That is a spontaneous emission. So we have the valence band and the conduction band. The electrons naturally return to their lower energy state and releasing a photon. This process is random and it's not useful for the laser action. And the next one is simultaneous emission. This is third process. It's simply the interaction of photon with an electron in the conduction band. It forces the recombination and thus the emission of a second photon. So when the excited electron hit by an electron photon of the same energy, it's forced to release the another identical photon. So this lead to a chain reaction, produces more and more photon of the same wavelength and same phase. Okay. And next one is the population inversion. In the population inversion, that redistribution of atomic energy levels that takes place in the system so that the laser action can occur. So again, I tell you, laser is a light amplification stimulated emission of radiation. Okay. So in this population inversion, the redistribution of an atomic energy level that takes place in the system so that the laser action can occur. Atom is temperature equilibrium, and more atoms in the low energy states, then the higher one is called population inversion. So this is the population inversion. And for the simultaneous emission to dominate over absorption, the population inversion is required where the more electron occupy the higher state than the lower state. This is achieved by pumping energy into the lasing medium. And these are the advantage of that absorption emission. So precise energy control. So precise energy control, it is used to selective excitation of atom in spectroscopy. And next one is the efficient energy transfer, the key for laser pumping mechanism. As I already said, the laser pumping into the lower state to the higher energy state. There is the electron move from the valence band to conduction band, then the flow occur. The last one is the tunable absorption. The different materials absorbs the different wavelengths, enabling the material specific application. Example, the medical treatments, solar cells, so like that. So in the line shape function, we consider three different mathematical description of the line shape for the absorb transition. The transition may be electronic, rotational, or vibrational, microwave, or infrared radiation. So these are the applications of absorption and the emission of laser, and identifies the spectroscopy, which is used to identify the material composition based on the absorption pattern, and optical pumping, the powers laser mediums like Rubé. And the next one is a solar cell, absorb the light efficiently to generate the electricity. The most of the light energy is converted into the electrical energy in the solar cells. And the biomedical imaging, it's a recently trend on biomedical imaging that the absorptive dyes enhance the contrast in the laser based imaging. So these are the major applications of laser. Thank you for watching.